coming to the CGD seminar joint with the Climate Variability and Change Working Group meeting. So it's my pleasure today to introduce our speaker, Marybeth Arcodia of Colorado State University's Department of Atmospheric Science, where she is a postdoctoral fellow in the Barnes Research Group. So Marybeth has a PhD in atmospheric science from the University of Miami and a Bachelor of Arts in Mathematics from Georgetown University. And point out really quick that at Miami, Marybeth was awarded first place in the 3-minute thesis competition in 2021. So be sure to ask her for that rundown at lunch after the seminar.
I don't know it anymore.
So as I said, she is a postdoctoral fellow focusing on climate variability and predictability on the subseasonal to decadal timescale, and is also interested in explainable machine learning applications, hence what she will be talking about today. She also has research interests in tropical and extratropical teleconnections, as well as actionable science related to sea level rise, coastal flooding, and hurricanes. And lastly, Marybeth is involved in institutional-led DEI efforts and sustainability initiatives. And if you are watching online, please note we will take questions at the end from the online audience utilizing Slido. And so if you just go to slido.com and then find the CGD seminar page, we will go between online questions and in-person questions at the end of Marybeth's talk. So thank you.
Thank you. Thanks, Monica, for the introduction. Okay. No. A podium mic? Hello? All right, maybe we fixed it?
Yeah, try one more time.
Hi, everybody. Okay, now everybody's awake. I know there's a lot going on today. Okay.
There we go.
Sorry about that. Thank you. Thank you for having me here today. And I'll be talking about decadal variability of subseasonal predictability, really kind of a mouthful of illities, but using explainable machine learning. So this will be the bulk of my talk, and this is work that I've done with my postdoc advisor, Libby Barnes, Kirsten Mayer, and collaborators at Lawrence Livermore National Lab. So the main motivation here is this subseasonal desert of predictability. The subseasonal timescale being between 2 weeks to 3 months, this bridge between weather and climate, but it has notably low forecast skill. But a number of consequential phenomena fall on this time period. Flooding, heat waves, droughts. So it's a really important time period to study, but to really increase this desert of predictability, this low forecast skill, we rely on predictable states of the climate system to improve these subseasonal forecasts. These are known as forecasts of opportunity. So to be able to make these forecasts of opportunity, we need to zoom out and really get a global picture. And so what I'll be focused on is this connection of the tropical conditions to the West Coast precipitation. So here we have the Madden-Julian oscillation propagating eastward from the maritime continent, and we can see that as it's propagating, it interacts with the jet stream, AR here standing for atmospheric rivers, and depending on where the MJO is in its cycle, it can lead to enhanced or decreased rainfall along the North American West Coast. This is occurring on subseasonal timescales. Now, when we look at a little bit longer at the ENSO cycle, we're now looking at the MJO on subseasonal, ENSO on interannual timescales for these sources of predictability. This combined influence especially has been shown to lead to forecasts of opportunity. So here we can see this is rainfall in the United States that's been filtered to just retain that subseasonal or MJO-related anomaly. And we see here in the Southeast United States, it's a negative contribution. We have an underlying La Nina situation. So here, these are MJO days in an active MJO during phases 6 and 7 that also had a La Nina going on. So then when we take just that La Nina signal, we see that expected dry signal in the Southeast US. This is then, these two signals constructively interfere, enhancing that dry signal in the southeast US. However, when we move into MJO phases 8 and 1, there's now a positive contribution from the MJO. This then destructively interferes with that dry signal from La Nina and weakens and actually reverses that La Nina signal during certain MJO phases. So now if we look on even longer time scales, we have these low frequency modulators of the North American West Coast precipitation. Here looking at the Pacific Decadal oscillation. During positive phase, we see drier conditions in the Pacific Northwest and wet conditions during a negative PDO. So putting this all together, we know that the tropics provide a source of mid-latitude subseasonal predictability for precip along the North American West Coast. And the Pacific Decadal oscillation modulates this rainfall variability on low frequency timescales. So this sets us up for our main research question, which is, does subseasonal predictability of precipitation driven by the tropics vary on decadal timescales? So to do this, I'll be using a machine learning approach called an artificial neural network. The basic idea here is you have some sort of input or data. It gets fed through this neural network, which is really good at recognizing nonlinear relationships, and then we make a prediction or an output. A little bit more in depth here. So you have this input and it's fed through the neural network, these hidden layers, to make a prediction. We then have a loss function that we're trying to optimize or minimize. We then move back through the neural network, updating those weights and biases. So this is an iterative process until the machine learning model is tuned or optimized for its prediction. Next, we're going to be using this machine learning to actually learn something about the climate system instead of just trying to make the best prediction possible. So here, let's say we're trying to output whether it's a 5, 6, or a 7. Well, associated with each output, the neural network also outputs a confidence associated with each output. So here we can see that the 7 has a 67% confidence or probability, and so this is the prediction that it will make. So using these neural networks, we quantify the confidence in the probability of the output. Next, we want to learn what did the neural network learn to make its decision. This is the explainable part. So a linear model here, it's inherently interpretable, so we can figure out what's going on. But a neural network, due to these nonlinear activation functions inside that black box, it's inherently not interpretable. And so this is where that black box notion of machine learning comes from. So we use these methods of explainable artificial intelligence, XAI. I'll also be using this interchangeably with explainable machine learning. And the goal here is to learn how the neural network made its prediction. So what was the decision strategy for making these predictions? And this is made using explanation or relevance heat maps. So for a fun example here, let's say we have this image of the bird, we feed it through the network, and it predicts a junco bird. Then we can go back into the network, open that black box, if you will, and we can make a relevance heat map to see what features the network learned to make its prediction. So we can see here the beak, the eye, the outline of the bird were actually really helpful for making the prediction. The reason that we use these explainable methods is to first gauge trust, build trust in our model, to make sure that we're learning real relationships that we expect to see about the climate system. We can also use these to fine-tune and optimize our models, do things more efficiently, maybe cheaper, and then ultimately to learn new science. And these two, the trust and learning new science, are really what I'll be utilizing here. So the data I'm using is from CESM2 from here at NCAR, so thank you. Large ensemble data set. I'm using 10 ensemble members from 1850 to 1950, the smooth biomass burning ensemble members, and I'm using November to March for the boreal winter, more active season of those tropical, extratropical teleconnections in the Northern Hemisphere. And I'm using daily anomalies calculated by removing the ensemble mean from those 10 ensemble members. Now, my neural network setup here. So I have training, validation, and testing data. So really for robustness of results, to make sure that we don't have just one really good, predictable ensemble member or one really unpredictable ensemble member, I train a series of 100 neural networks. So the first 10 neural networks take 8 ensemble members, and then 1 validation member, 1 test member. Then we shift forward. So I take another set of 8 training members, 1 validation member, 1 test member, and then repeat for 10 different iterations of this. So my neural network setup here, so I'm taking daily tropical precipitation maps. So each point here, each grid point is a predictor, and I'm taking every day from November to March, 1850 to 1950, and I'm making a prediction for the week 3 to 4 average precip anomaly in these 5 regions along the west coast of North America. Canada actually turns out to be not that exciting, unfortunately. So I'll really focus on Alaska, Pacific Northwest, and California here. So the goal here is to predict the week 3 to 4 precipitation anomaly along the North American West Coast using daily precipitation anomalies from the tropics as my predictor. So first we want to know, are our neural networks learning something real? So each of these is that test ensemble member, so these are independently trained. The black diamonds here, you can see that they're kind of clustered. Each of these represents a random seed of the same network. So this is just a random initialization of that model, again for robustness, to make sure that the model is learning the same thing over and over. And so we can see here that this is the overall accuracy from that 100 years of predictions. And there's some variability here based on ensemble member, but we then compare this to an untrained model, and that's these gray X's here, each of these representing a random seed. And our trained neural networks are distinct from that random model. So we are now confident that we have in fact learned something real about the climate system that these models have picked up on. So next, going back to quantifying the confidence of the neural network prediction. So we're ranking, so if you remember, we had that probability or confidence output with our predictions. So now we can rank all of our predictions by confidence. So here, this is all of our predictions, 100% of the predictions. And then moving along the x-axis, we're up here to the 10% most confident. This was an application first used by Kirsten Mayer and Libby Barnes back in 2021. And we also see that as we move, as we increase our confidence, we also increase our accuracy. So if we say, look at just the 20% most confident predictions, these are also our most accurate predictions. So by definition, these are more predictable time periods or forecasts of opportunity. So now looking, what did the neural network learn? So the XAI technique I'll be using here is called integrated gradients. It's an attribution technique. So this means that we can quantify the relative contribution of each input feature to the output. So we can see basically how important each grid point on the map was to making the prediction. Then I take those heat maps and I use k-means clustering. It's an unsupervised form of machine learning where we're grouping the data into clusters based on similarities. So here we have this integrated gradients XAI heat map where the darker purple colors here mean more relevant to the contribution. The oranges or yellows here actually mean that it negatively contributed. So we see here that these are the 20% most confident, which by definition are also the most accurate or our forecasts of opportunity. And when we cluster the most relevant or most important features, we see some hotspots pop out here. These are for our negative predictions in Alaska. So here, this Western Pacific, usually linked with an ENSO signal, is really important. We also see here that the west of the maritime continent and also the north of the maritime continent, MJO regions, also are pretty important, as well as this region out near Hawaii. And then also we see a little bit here near South America. Now this gets back at that building trust in our model as well. We know that MJO and ENSO have teleconnections, especially in boreal winter, to the mid-latitudes. And so the fact that our neural network is picking up on these regions means that, one, these are not only sources of predictability for the model, but also we are building trust. We are confirming that the model has learned something real about the climate system. Then we can look for additional sources of predictability, say this spot out near Hawaii that's been shown in a few other studies, but then also this near South America. I'm not so sure about this. If people have ideas about this, I'd love to hear them about how this area could be affecting Alaskan rainfall. Could be spurious, maybe it's something new. Definitely want to look more into that. But this is where this explainable AI is helping us learn more about the climate system, these sources of predictability. These are the number of predictions that went into each of these clusters. And then just looking again here at the positive predictions, we see a similar type regions for these sources of predictability, although the maritime continent and this Hawaiian region don't seem to be as relevant. So now this was for Alaska, so now we're looking at California and the Pacific Northwest. This is the same analysis that we did for Alaska. So here, again, these are each of our ensemble members. Each of these black diamonds is a random seed, and we see that the accuracy is, again, above random chance. And we actually have a bit higher accuracy for the Pacific Northwest than California. And we also rank by confidence here. And here I'm just taking one ensemble member from each as an example, but we can see that for both of these regions, we're identifying these forecasts of opportunity. Now, we can also look back into the inputs themselves to see also what was important for making this prediction to look for these sources of predictability. So going back to Alaska here, we have the correct 20% most confident predictions. And this is a composite of the input for a negative prediction in Alaska. And here's the same, but for a positive prediction. So we see this La Nina type signal associated with a negative anomaly in Alaska, and a La Nina type signal, opposite, El Nino type signal for a positive anomaly in Alaska. Now, if we look at the 20% most confident but incorrect predictions, meaning the model had high confidence but was actually wrong in its prediction, we actually see the opposite pattern here. And so what this means is that the model has learned, which we also saw from those XAI maps, that this tropical West Pacific maritime continent region is important for making the prediction. But if, say, a La Nina is present, the model is going to be confident in predicting a negative anomaly in Alaska. But if it's a La Nina, but it's actually a positive anomaly in Alaska, it's going to be confident but wrong. When we look at California, it actually has a very similar teleconnection pattern. Negative precip anomaly associated with a negative California anomaly and vice versa. We see the same situation for the incorrect predictions. Then when we look at the Pacific Northwest, it is actually this opposite pattern. And so this actually is in line with our understanding of ENSO teleconnections and meridional shifts in the jet stream. And so by given just these daily tropical precipitation maps, our neural networks have actually learned this shift in the jet based on the precip anomaly in this tropical West Pacific maritime continent region. So now getting at that decadal variability. So that research question of, does subseasonal predictability of precipitation driven by the tropics vary on decadal timescales? So now what I've done here is separate those 20% most confident, those forecasts of opportunity, and then also the 20% least confident in gray here. Each of these lines represents those random seeds, with the darker line being the mean here. And so we see here that if we look at the least confident predictions, it really wiggles right around 50% of random chance. However, when we look at the 20% most confident predictions, we actually see that there is, in fact, this low frequency variability. And let me explain here. So this is a 10-year moving window of the accuracy. And so here, this is 1851 to 1860, the accuracy just over that time period. We shift forward 1 year. 1852 to 1861. And then this is that accuracy that we see plotted here. And then we also see that we have these certain low frequency time periods that have this really high predictive skill and forecast confidence. Again, getting at those forecasts of opportunity, or that increased predictability. I lost my other blue circle here, but we're also going to compare this to our lowest accuracy for the most confident predictions. Why are there certain time periods when the model is confident and correct, and confident and wrong? And then this is just to show here, this was the one I showed in the last example. This is for all the ensemble members, and we see various degrees of this variability in all of our ensemble members. So I take this highest period of accuracy and compare it to the lowest period of accuracy in 10-year chunks for each of the ensemble members. So then to investigate these low frequency drivers, we take this binomial statistics approach to see how often the PDO was in a certain phase during each of those high and low accuracy time periods. So when Alaska had a negative precipitation anomaly, and this is in that high accuracy period for our forecasts of opportunity, 2/3 of the time, the PDO was in a negative phase. And then vice versa, when there was a positive anomaly in Alaska, 2/3 of the time, the PDO was in a positive phase. If we then compare this with those low accuracy time periods, we see that either there's not really any signal from the PDO, or it's actually the opposite. And so this is really getting that the PDO is modulating these low frequency time periods of when the mid-latitudes are teleconnected to the tropics. And so we're looking now at these low frequency predictable states of the climate system. So now this is looking at California. Again, here we take the highest 10-year periods from each of these ensemble members and compare them with the lowest accuracy for the most confident. And now we see here the story is a little bit clearer, but for the positive precipitation anomalies. So here we saw that same sign relationship in California, and we see this here with the PDO, but the story's not as clear for the rest of the predictions. We do a similar analysis now for the Pacific Northwest. But if you remember, it was the opposite relationship of an inverse relationship between the precip sign in the tropics and the precip sign in the Pacific Northwest. And that's again what we see here for the positive precipitation anomaly. So then, how am I doing on time? Okay. So then we wanted to see, all of this was trained in CESM2 model world. So we wanted to see if we could actually extend this to the real world. So without retraining any of our models, we take just those pre-trained networks for Alaska, and we feed it ERA 5 data from 1959 to 2021. We do the same analysis here, and the red line here showing 20% most confident predictions. Gray is the 20% least confident predictions. And we see here that the decadal variability of that predictability still holds. And so what this means is that the network learned a real and detectable signal in the climate system. So I just want to emphasize here that the CESM models were trained 1850 to 1950 specifically to avoid a climate change signal, even though we removed the trend with the ensemble meme. But with ERA 5, we used the most recent data. We still took the anomalies, but it's still learning this signal here. And so, and this is without pre-training. And so again, this is looking at those signals at those sources of predictability that our networks have actually learned. So to summarize this part, we used artificial neural networks to quantify predictability from the tropics of weeks 3 to 4 West Coast precipitation anomalies. Using daily tropical precipitation anomalies as our input, we feed this through our neural network to predict the week 3 to 4 output. We found that there is decadal variability in subseasonal predictive skill. We identified forecasts of opportunity and sources of tropical subseasonal predictability, and this analysis was then extended to ERA 5 data. We found that the PDO is modulating those low-frequency time periods of when the tropics are teleconnected to the extratropics. So this is highlighting those low-frequency predictable states of the climate system, but it is definitely going to be exciting to look more into why are there time periods that are more teleconnected than others. That also varies by region. So some ongoing and future work that we have here is investigating more of these sources of subseasonal predictability. So the first is using global sea surface salinity as predictor for regional subseasonal rainfall. And so here is a schematic where we see that most of the water that evaporates over the ocean rains back out over the ocean. But about 10% of that water vapor is actually transported over land. And so we want to use these similar explainable machine learning techniques to see if we have additional sources of predictability by using sea surface salinity anomalies. So the idea here is a similar setup, but instead of using tropical precip maps, we're now using global sea surface salinity maps to make predictions. Here's an example. I have summertime in the Midwest, because this has been shown to have some seasonal predictability, but we want to look at how this predictability varies both in time on subseasonal. Whoops.
If you click the mouse button once, it
Okay. Expand this. So we want to expand this into more regions and also different timescales from subseasonal out to seasonal. And then we're also looking, the work that I've shown so far was all using artificial neural networks. And so we've also been exploring using convolutional neural networks, which is a branch of artificial neural networks that takes in images for detection. We're also looking for sources of predictability for subseasonal regional sea level extremes. And so here, this is showing the flooding days in Virginia Key or Miami. These black bars here are showing observed flooding days per year historically. Then each of these is showing a different regionalized sea level rise projection scenario, minimal mitigation through extensive mitigation, or our SSP scenarios. And we can see here that under each of these scenarios, even this extensive mitigation scenario, we're at over about half of days per year flooding in Miami. This is coastal flooding, nuisance flooding, sunny sky flooding. And so the IPCC has reported that we can expect more frequent and intense coastal flooding with climate change. However, we also know that there's internal variability that plays a role in regional sea level. And so this in a study that I just finished up, kind of submitted, we are looking at MJO and ENSO influences on US rainfall, but there's been a number of studies looking at different internal modes of variability that can affect rainfall. So we want to ask, can we use these explainable machine learning techniques to identify large-scale predictors for regional sea levels that can potentially lead to extreme events? And then also these internal variability modes can also mask some of the sea level rise trends that then when we shift into, say, an accelerated mode, could actually exacerbate them. And so these are ongoing works, and so I'd love to hear thoughts people have, ideas, collaborations, anything like that. So just to wrap up here, we've used explainable machine learning to, one, detect decadal variability in our subseasonal predictive skill. We've identified forecasts of opportunity by leveraging our machine learning models to quantify the confidence in our outputs. And we've also used these explainable machine learning techniques to highlight sources of subseasonal predictability. Thank you very much, and I will take questions.
Okay, thank you. So I'd like to open it up for any in-person questions that we might have. If you just raise your hand, I'll come around with the microphone. And then with respect to online participants, if you just want to put your questions in Slido. Okay.
Thanks, great talk. I was just wondering about the role of the PDO in the ERA 5 results. So you showed that you argued the PDO was very important for the CSM results. Is that time series that you had for ERA 5 of when things are predictable, does that correspond to the PDO as well?
Yeah, so that is definitely something I want to basically do is like the same analysis, but for that ERA 5. However, the PDO index from ERA 5 is actually like slightly inversely related. However, for those time series of accuracy, here we go. So let's say here. So these are the time series of that 10-year running window of the accuracy. We correlated these with the PDO index, the ENSO index, NAO, PNA. But there was no real consistent correlation. And the reason this is, I'm pretty sure, is because this is showing the accuracy, which can be high based on positive and negative predictions that were associated with a positive or negative PDO, based on if that teleconnection was present. And the PDO index is just showing positive or negative. So by looking at just a correlation between the index itself and the accuracy is not really as telling. We also look to see if when the PDO and ENSO were in phase, if that led to higher accuracy, but that also didn't really show consistent results. Again, I think because it's more of this teleconnection that's actually present from the tropics to the extratropics. So that signal is there in the tropics, but is that actually teleconnected? And so looking at that in ERA 5, especially because we have that historical data, the recent data, I definitely want to look at more.
Okay, did you have a question?
Thanks for an interesting talk. So I was wanting to ask a bit about the mechanistic understanding of this decadal variability and the predictability. So just thinking that there's probably something to do with the different state of the North Pacific jet in whether you get this teleconnection from the tropics to the West Coast. And I was just wondering if you have thoughts on whether this is showing, so the role of the PDO being, is this a passive indicator of what the state of the jet is, or do you think it is influencing the atmospheric circulation in a way that then influences the presence or not of the teleconnection?
The first. So this is more of the state that the PDO is setting up as a way to quantify the different predictions that were being made. So again, this neural network is only getting fed daily precip maps of the tropics, so 26 south to 26 north. So it's not actually getting directly any PDO information. It would be in a PDO modulation of the daily tropical precip that it's picking up on. So more so, instead of being this deterministic predictor, it's setting up a more predictable state of when that teleconnection is present. And so as you got at the North Pacific jet, is my guess as to the culprit here. So if the jet is actually, and if we saw from that MJO schematic at the beginning, if the jet is more directed towards Alaska, say, and that teleconnection is present, then we're going to see those high accuracy, high confidence, while if the jet is, say, elongated and moving more into California or Canada, then that teleconnection wouldn't be present. And so, as you said, it's really the state that is being set up by the low frequency variability for the predictable time periods.
Okay, thank you. So we have quite a few questions online. So I'm going to take one or two of those, and then I'll get to Clara and some other people in the room. So Danielle Tumo says, really cool work. By detrending your time series, did you remove any ability to understand how warming or other external forcing could impact predictability, or is that embedded in your analysis somehow?
So we hopefully did remove any sort of climate change signal. That was the goal. And so that was also the motivation behind using 1850 to 1950 as opposed to more recent years. So we wanted to look at just internal variability here. And I will say that we did this same analysis on the pre-industrial control run, the 1,000 years from that pre-industrial control, and we see very similar results here. So we are confident that we've effectively removed the forced response. Now, looking at this analysis, but under climate change scenarios, is definitely somewhere that I would love to see this work go, to see how these relationships will change, and also to see if we have enhanced or decreased variability, low frequency variability of the predictive skill.
Okay, thank you. And one more from online. So Dan Amrine would like to say, thanks for a clear and interesting talk. Do you think that if you regress the PDO out of your data that the modulation of subseasonal predictability would change? Maybe related, can you comment on how much of the predictability changes might come from changes in persistence?
So the first question, no, I don't think so, because again of what the input is to the neural network. So it would be more so if we regressed it out and it somehow was able to remove the precipitation daily variations. So instead, the PDO is more, we're using the PDO to set the stage of the difference between the high accuracy and low accuracy. So I don't expect that would cause, that would change the results very much. Could you repeat the second question? Sorry.
That's okay. I might actually turn it over to Clara because I
Okay.
dismissed that one on accident. Dan, we'll get back to you in a second.
Thanks for your talk. You showed the heat maps,
Mhm.
and you mentioned there was something over the tropical Atlantic and tropical Indian Ocean. You don't have to show it, but I was just wondering, is there a way to use these neural networks to really get at what is causal in these heat maps? Because to me, the Atlantic signal could just be part of, this sort of well-known ENSO pattern that doesn't directly relate to how the circulation affects rainfall on the west coast of the US. So is there a way, like learning the bird, the junco? I mean, it's, there can be non-causal aspects of this heat map. Have you thought about how One
Yeah,
good one?
that's a great point. That this may just be related to the overall signal that we're seeing anyway, and that the model is picking up on that. That's absolutely true. So we haven't done any sort of causal discovery here, but it's definitely something that we could do of using these causal approaches to look to see really like, did A affect B, that type of relationship. So that could definitely be applied here. The other thing I think could be using this like idealized modeling approach. And so say input some sort of forcing in just this South American region to see if we get even any response in Alaska, or if we would need this full signal, potentially like expanded to some sort of hierarchical model approach. But that would be the other way I would think to really like investigate that as a source of predictability.
Hi, Marybeth. Thanks for the great talk. So the input of your network ranges from March through, or sorry, early
November
season to
through
late
March.
season. Yeah, November through March. But there's been a lot of work showing that the teleconnection is modulated pretty significantly, both for MJO and ENSO across that season, which can lead to different precipitation patterns. Have you considered splitting early season, late season, or have you looked at any of the sort of subseasonal variability just in teleconnection itself to see if that improves skill or takes away from skill, and how it sort of changes as it moves across that season?
Yeah, that's a great idea. I think the one caveat to that is that the data hungry aspect of machine learning. So we're using 10 ensembles here for the 5 seasons, 5 months, November through March. And so by splitting that, as far as predictions go, we would lose some of that data. However, we could just analyze, like for example, make these heat maps for early season versus late season. That's a great idea. The other thing is looking at additional seasons is for that sea surface salinity that I talked about at the end. We're actually focusing that on the summer season because that's some of the prior work has been shown for the summer. And so kind of looking at different sources of predictability, but across the seasons. But I like the idea of separating this a little bit more by early and late winter.
Okay, and Hyen online would like to know if PDO can affect the subseasonal predictability through tropical, extratropical teleconnection. Do you expect stronger impact from ENSO through the same mechanism?
So I think if I am understanding the question correctly, it's more so that the PDO is setting up a state of where the teleconnection is present or not. And so the ENSO, now this is the ENSO region here, but this is really what the model has learned. And it's making these subseasonal predictions, and this is really coming from this MJO region, this maritime continent, Indian Ocean. So the ENSO or West Pacific region is what the model's learned, and that's where it looks to make its predictions, especially for when it's confident. So when it's confident and wrong, it's looking here, and when it's confident and right, which is what we see here, it's also looking here, so relevant. The PDO, or the low frequency state, is more determining if the teleconnection to the mid-latitude is actually present.
Okay, thank you. And then another one from online, Sanjeev Kumar says, great presentation. Is the climate model biases built into the ML AI model? So is ENSO teleconnection is stronger in CSM than observed, at least for California? Does that impact your interpretation? And then a larger question, how does the AI machine learning approach help us to understand and possibly correct climate model biases?
So first is yes, this is all using CESM data, and so biases that are in the model will be in these results. However, because of that, that's why we use 10 ensemble members. That's why we use this 100 neural network setup of 10 models, each with a different test member, different training, different validation, to see for consistencies across the results here. And so looking at these heat maps, for example, this is to look at for consistent sources of predictability. Now, this is within CESM, but we're looking to see what is consistent across ensemble members, removing this forced response to help get at real signals in the climate system. This is also why we extended it to the ERA 5 analysis, and we still did see some of that decadal variability. The XAI for learning model biases, yes, that is work that is definitely ongoing in the field to be able to predict and detect model biases and correct for these. Will was telling me this morning about some techniques that he's using for model biases. So it's not something that I've shown here, but it's definitely ongoing research.
Yeah, I'm just curious what your rationale is for using just tropical daily precipitation as your predictor. I mean, why not throw as much information as you can and use daily SST, for example, or daily ocean heat content, or something that would potentially add predictability, and also if PDO is relevant, then that would show up in your heat maps for SST, I would think.
Yes, I completely agree. However, this is, like a cost benefit type thing. So by starting, so this is the tropical maps, as you said. The training on the global sea surface salinity tripled my training time for just one random seed of training. So it's really just so expensive, especially with these amounts of ensemble members. We also wanted to look for tropical sources of predictability. I think ideally it's kind of like, it's similar to thinking like, wouldn't it be great if we had infinite resolution of a climate model? I would love to be able to train lots of neural networks globally, high resolution, lots of predictors, and be able to parse them apart. But one, from an interpretation standpoint, it makes it harder the more things that you then need to explain, and two, just from a computational expense.
Okay, thank you. So Cecile Penland online would like to know, what about the Southern Hemisphere? Rossby waves generated in the Indian Ocean can affect trades in the Atlantic as well as ENSO. So that Atlantic acts as a predictor of Northern Hemisphere precipitation, but there's no causal connection. ENSO affects Northern Hemisphere precipitation, but the signal is in the Western Atlantic first. I guess.
Yeah,
yeah,
definitely. This is looking at the tropical Northern Hemisphere, North American teleconnection. And I would love to look at this also in the Southern Hemisphere, also to compare the sources of predictability and also to compare the accuracy. This is something that we are planning on doing with the salinity and sea level analysis. Maybe would be great to also extend this precip analysis. And so looking again at these like global the sources of predictability, but for regional subseasonal forecasts is something that we hope to be doing soon.
Okay, and Rich Neal, sorry, there's quite a few that came in online. So
great.
Rich Neal says, nice talk. It's interesting that there is not much heat in the Indian Ocean, the start point for most MJOs. Would there be if you looked at 5 to 6 weeks precipitation on the West Coast, for example?
Heat, I'm guessing like heat maps from here. And yes, so there's no direct input of the MJO here. There's no like MJO filtering or anything like that, looking active, inactive. Instead, these are again just those daily precip maps. So it is interesting that the maritime continent, like in MJO 5-6 phase, 4, 5, 6, 7 phase is showing up more. That is a like great hypothesis about like looking even maybe week 1, 2, or week 5, 6 to see if this region would light up more. But in a lot of these heat maps that I looked at, positive, negative, the different regions that we predicted for, the Indian Ocean was not as important. So yeah, maybe.
Yeah, I guess I'm I'm still a little confused, and I had somewhat similar question to what Clara had. So I guess when I look at the precip heat maps, it looks like all ENSO to me, because this model certainly shifts the ENSO response well into the Indian Ocean. So I'm not quite sure how you're separating ENSO and the MJO in these heat maps. And I don't entirely understand where the PDO is coming from either, because all you have is a kind of an ENSO precip pattern. So couldn't your variations in skill just be kind of random variations in ENSO amplitude?
Yes. So it could well be that. However, so there are no indices that are going into this model. Instead, like, these are just the standard way of describing them. Like you said, this looks like ENSO, but the model isn't given any direct information about it. The reason that we say that it's not just using the ENSO state is because when we look at the individual predictions, it's making subseasonal predictions. So it's changing from days to weeks. While if it was just learning the ENSO state, it would be basically making the same prediction for every season. So if the model learned to look in this Western Pacific, there was a La Nina going on, it would make 3 months worth of predictions of negative precipitation anomalies. But that's not what we see when we're actually looking at the individual predictions, which is why we're looking more at this MJO-like setup here for the subseasonal prediction and the additional influence. As far as the PDO goes, it's more so getting at the state. So like you said, of the teleconnection being set up, and we use the PDO to actually quantify the difference in the predictions. And so whether the PDO is directly modulating it, I would actually argue that it's not, because we didn't see that it was consistent amongst all of the different binomial charts that I showed. Instead, it was a way to show these low frequency changes to the predictive skill for confidence.
Okay, and I think we have one remaining in-person question, and then we'll probably be at the top of the hour. So you get the last word.
Thank you. It was a very interesting presentation. For your ERA 5 results, you also should have access to reforecasts with IFS model for ERA 5. Do you see the same variability in practical predictability from reforecast as you see from your, theoretical predictability results from your neural network?
That's not something I've looked at, but I really would love to be able to apply this type of analysis to the reforecasts and also analyze the skills. So maybe one day.
Okay, thank you. So let's thank Marybeth one last time.
Thank you. Thanks for having me. And thanks for all the questions.
Yeah, that was a great discussion. Thank you for everybody who brought questions. If you are part of the Climate Variability and Change Working Group, I believe you guys resume back in this room at 1 p.m. And we will see you next week for another CGD seminar. Thank you.